Hello students, now I will tell you the radiation distribution curves of a black body. Radiation distribution curves of a black body. Radiation energy distribution curves of a black body. These curves were obtained by Loomer and Princeton. So this is one like this, that here we have a mirror. This is a black body. This is black body. This is a prism. Mirror M1. This heat radiation from here goes on this mirror. Here is this is the bolometer. This is mirror M2. This is concave mirror. This is rock salt prism. This is the again a concave mirror. And this is the bolometer. Here this is the black body. When this black body is heated, it emits the radiation. These radiation go to the mirror M1. From where they are reflected, and then they pass to the rock salt prism. After passing through this one, the heat radiation goes to the concave mirror M2. Now from here, this is again reflected and goes to bolometer, and bolometer measures the intensity of the heat radiation. Bolometer measures the intensity of heat radiation. So this is the practical arrangement. Experimental arrangement. So what they were obtained by Loomer and Princeton. Now the curves are like this. This is E lambda and this is now lambda. The curves like this. We will have these peaks here. This is suppose now temperature T1, this is T2, this is T3, this is T4. So this T4 greater than T3 greater than T2 greater than T1. So temperature is in the increasing order. And this is the E lambda, the spectral emissivity power of the body. So these are the curves of energy. These are the energy distribution curves. These are energy distribution curves at different temperatures. Of black body. Black body. So these curves have certain properties. Now you see that this is the peak. So first you can see readily that these energy distribution curves are continuous. Initially at a given temperature, the E lambda increases with the increase of lambda and gains a maximum value at the peak, and then E lambda decreases with the increase of lambda. And you can see that the area below each of the curve will give you the total amount of heat radiation emitted by the body. And also you are looking at as the temperature is increased, the peaks of the curves goes towards the lower wavelength side. This is not so much, then this is increasing, decreasing like this. Properties of radiation curves. Number one, the energy distribution curves are continuous curves. Second, at a given temperature, initially the value of E lambda increases with the increase of lambda and gains maximum value. After which the value of E lambda decreases with the increase of lambda. At the given temperature, you can see either of the curve. For each of the curve, temperature is constant. So for a given temperature, initially the value of E lambda increases with the increase of lambda. You see that curve goes like this and gains the maximum value, after which the value of E lambda decreases. So first it goes like this and then it decreases like this. Decreases with the increase of lambda. So it means that at the peak, the energy distribution is maximum. At the peak of curve, E lambda is maximum and is proportional to fifth power of temperature. It means that this E lambda proportional to T to the power 5. This is what the meaning of this one. This is only at the peak of the curve, not anywhere else. And now third, the peaks of curves shifts towards lower wavelength as the temperature increases. We have seen that as the temperature increases T1, T2, T3, T4, the peaks of this curve goes towards the lower wavelength. The peaks of the curve shifts towards the lower wavelength as the temperature increases. The wavelength corresponding to peak of curves is inversely proportional to the temperature. The wavelength corresponding to peak of the curves is inversely proportional to the temperature. It means lambda m is inversely proportional to 1 upon T, and this you can see that this is suppose lambda m, this is now a temperature, then this will be like this. So lambda m proportional to 1 upon T, because as the temperature increases, the peak of the peaks of the curves goes towards the lower wavelength. So lambda m means the lower wavelength or the minimum wavelength, or lambda m equal to b upon T, or lambda m into T equal to b, where b equal to Wien's constant. It is 2898 micrometer Kelvin. It is called Wien's displacement law, and this law is valid only for lower wavelengths. It is valid to low wavelengths. So this gives you the Wien's displacement law, which goes to the lower wavelengths, and this law is well applicable to the bodies like the all the sun and stars, and that of the suppose we have the furnace. Then if we know the value of lambda m, you can calculate the value of T, the temperature of the body. Now fifth, the area under each curve gives total amount of heat radiation emitted by the body. The area under each curve gives the total amount of heat radiation emitted by body at the given temperature. At given temperature. So it is found that this area the area under each curve is proportional to fourth power of temperature. It means that E is proportional to T to the power 4. It is Stephen's law. It proves Stephen's law. And you can have that on the lower balance side we will have the Wien's law. But for longer wavelength side, longer wavelength E lambda d lambda equal to 8 pi kt upon lambda to the power 4 d lambda. It is called Rayleigh-Jeans law. It means that to explain whole of the curve, first you have to take the help of Wien's displacement law, and then for longer wavelength you have to take the help of this Rayleigh and Jeans law. Now here this K is Boltzmann constant, T the temperature, Vm, K Boltzmann constant. Thus the whole of the curve has the two laws. First the Wien's displacement law, and then this Rayleigh and Jeans law. So these are the properties of the energy distribution curves, and also I show you that how these curves have the area, what does it represent, and what is the peak value, and what is the relation for the temperature of this one, and also it verifies the law of Stephen's law of radiation. So you like and share and subscribe the video. Thank you.